Dear students, friends and learners, I am Shashank Srivastava from School of Engineering and Technology, Indira Gandhi National Open University. So today we shall be discussing about the Unit 2 again, but the modules are changed now. In this module, we shall be discussing about the alloy steels. So there are important alloy steels. The first one which we are now going to discuss is the structural steel. So these alloy steels, there are low alloy steels also, and these are used for structural purposes. And these steels are required to possess high yield stress, good ductility and high fatigue resistance. Why? Because good yield stress will lead to good ductility, and with good ductility the structural will not fail in one go, like in case of the brittleness. So ductility is very important, and also fatigue resistance is very important, because there are different kinds of loads which these structures have to bear. So like the wind loading and all those, so we need to have high fatigue resistance. Then the high yield stresses will result in direct weight saving also in part of the structure. Now when we are talking about low alloy structural steel, so we should also know about what is its composition. So here it is, it contains carbon which is 0.12%, manganese 0.75%, silicon 0.25% and copper 0.3%, and the rest is iron. So you can see here that the carbon percentage is very less, 0.12%. That means it almost comes under the category of ferrite, which you have studied earlier. So it is a little softer, and softness we need, because then only ductility can come in. So its properties are like this. It has a high yield strength of 350 Newton per millimeter square, and it has a 15% elongation after hot rolling. When the rolling process is done, it will have 15% elongation, and then copper in it will improve the corrosion resistance, and further manganese and silicon improve the weldability. And how do they improve the weldability? By preventing the weld embrittlement. So this manganese and silicon are important, and weldability, like you would be knowing about the welding processes. So wherever we need this, so in that case, if Mn and Si are there, then we can prevent the brittleness of the structure. Further, small amounts of nickel, chromium and vanadium, when added to these steels, will improve the yield strength, and they improve it to 625 Newton per millimeter square, which is about the double which we saw initially. It was 350 around, and if you double it or you multiply by 1.8, then you get around 625. So you can see that how much the yield strength has gone higher if used in quenched and tempered conditions. So this is the case when it is used in quenched and tempered conditions. And furthermore, additions of nickel, chromium and vanadium do not affect the weldability. After discussing the structural this steel, we shall now discuss about the stainless steel. So the best property of this kind of steel is resistant to corrosion. And why it is so? The reason behind that, because what happens in this case is that a protective chromium oxide layer is formed, and this chromium, if present in large proportions, helps to form this layer and thus spreads all over the surface. Then what happens? This layer does not allow the surrounding atmosphere to further react with the steel, which retains its luster and appearance. So this layer of chromium oxide prevents steel to react with other things, so its appearance remains as such. This oxide film is impervious to both metal ions and atmospheric oxygen. So it helps, this layer helps to prevent the metal ions to get into the this structure of steel. So further, how we can improve this corrosion resistance in SS, that is a stainless steel? Same thing, that we have to have the greater percentage or increasing percentage of chromium. But a condition is there that chromium should be in solid solution and not combined as carbide, because carbide will lead to hardness, and it will not lead to corrosion prevention. So that is the requirement, that chromium should be in solid solution. The corrosion resistance further will be enhanced by addition of certain amounts of nickel. Like we have already studied in the previous sessions that nickel helps in corrosion prevention. So again it is seen here. After discussing the stainless steels, let us now see the classification of that. So according to structures obtainable at room temperatures, the stainless steel is subdivided into three groups, that is ferritic, austenitic and martensitic. So these are the three subdivisions of stainless steel. So first of all we discuss the ferritic one, and its composition here it is given. It contains chromium as alloying element in addition to a small percentage of carbon. Carbon is from 0.05% to 0.15% and chromium is from 13% to 30%. So when we are talking about ferritic, we know that it is softer in nature, so it has to be in the alpha phase. It contains only alpha phase at all temperatures. Some chromium precipitates in form of carbides along with ferritic grains at room temperature. So it also contains some chromium precipitates which are in the form of carbides, and these are like a kind of a mixture with ferritic grains, and they are at room temperature. So the properties of this ferrite, it is very ductile. As we know, it is soft, so it is ductile, and it has excellent resistance to corrosion. And where it is used, where it is employed, applications, the use are like this. They have outstanding formability in complicated shapes, and many deep drawn objects are produced from ferritic stainless steel. So deep drawn objects, like you study in your manufacturing science when you have to suppose make a wire, so it is also produced by the deep drawing effect. So these are the deep drawn objects. So ferritic stainless steel is very important and usable in that case. Further on, the second type is the austenitic stainless steel, and the conditions for that to prepare it are like chromium plus nickel should be 24%. The sum of chromium and nickel should add up to 24%, and at the same time chromium should be more than 8% and nickel should also be more than 8%. So it cannot be like, suppose chromium is 4% and nickel is 20%, so total will be again 24%, but our criteria that both chromium and nickel more than 8% will not be met. So both these conditions have to be met. So in the process, it is now quenched from upper critical temperature. So upper critical temperature, as you know, it was around 900 degrees centigrade. So it is quenched from that temperature, and then it is retained on cooling at normal rates. Composition is like this: 18% chromium, 8% nickel and 0.1% of carbon. So it is also called 18-8 steel and is most commonly used. Its applications are in like construction of chemical plants, decorative purposes and household utensils. So you see in your kitchens and all, so these things are made of austenitic SS, and even in the chemical plants, if you see different kinds of this material storing boxes and all, these are also made of this austenitic SS. So the last classification is the martensitic SS, and the conditions for production are as such: chromium and nickel should be in such proportions that steel has a gamma phase at high temperature. That means the mixture of chromium and nickel proportion should be such that only austenite is there at high temperature, and an alpha phase on cooling at normal rate. So when we cool this austenite type, it should go into the ferritic type, that is alpha phase on cooling. That is the condition. And why it is needed? So that it can be quenched to give a martensitic structure. Such heat treatable steels are known as martensitic steels even when not in heat treated conditions. And the process for this is that it will be oil quenched from above upper critical temperature. So 900 degrees centigrade again, and there will be oil quenching, not water quenching. The types of this martensitic type of stainless steel and its applications now. So there are three types of martensitic steels available commercially. First one, you can see the difference between these is only on the basis of the carbon percentage and the chromium percentage. First you see 0.07% to 0.1% of carbon, 13% of chromium. Then 0.2 to 0.4% of carbon is the second one, 13% chromium, and the third one is 0.1% carbon only with chromium 18% and nickel also coming in as 2%. And applications, vast applications like in the turbine blades. So you see in the jet engines and other places, even the steam turbines, so they are used there, very useful. Surgical instruments also in the medical field, so martensitic steel is used there. Springs, ball bearings, pump shafts, aircraft fittings, etc. So a very useful product, this one is martensitic type of stainless steel. Now we will compare between the different types of stainless steels. So martensitic steel can be heat treated to obtain high strengths. So this is the property of the martensitic steel. Further, the strength of ferritic and austenitic steel can also be improved, but it can be done only through mechanical working. And one example of that mechanical working is that various precipitation hardening stainless steels, these are the ones which are developed by the mechanical working process. So now we see that SS is very good, but we face welding difficulties in case of SS, stainless steel. Now we will see why it happens and what is the temperature range and all. Like in high temperature range 500 to 700 degrees centigrade, the stainless steels lose their resistance to corrosion. So even SS will lose its corrosion resistant properties at a temperature of 500 to 700 degrees centigrade. And reason is that the chromium in the SS will have a tendency to separate from solid solution and precipitate in form of carbides at grain boundaries. So this chromium carbide will be formed and it is posing all the kinds of difficulties. Thus welding of the stainless steel becomes difficult and causes what is known as the weld decay, because due to chromium carbide hardness comes in, so the problem arises. And what will be the solution for this? So if the welded part is reheated to a temperature of about 900 to 1000 degrees centigrade, so it is around the same temperature as the upper critical temperature, then the carbides are redissolved and can be converted into a stable solid solution on quenching. So we are, you can say, going into the austenitic region. So carbides are redissolved and no chromium carbide will be formed, and then we can have a stable solid solution. Further, we discuss now the high carbon tool steel. We have now come to tool steel. What is the composition of this tool steel and where it is used? So it is used to shape, deform or cut other materials. So if you have to cut some material with another material, the material which is cutting the other material should be of good properties and should be hard also, then only it can cut the other material. So the common tool steels contain what? Carbon, tungsten, chromium, molybdenum, vanadium, manganese, silicon. So many of the elements are present and they are generally present in the range of 0.6 to 1%. And what are the properties of these high carbon tool steels? Like I said before, hardness and wear resistance is one of the main properties, and then it should have shock resistance also, because suppose you are working on a lathe, so when you are cutting something, vibrations will be there, shocks will be there, so it has to have shock resistance. So for that, carbon is restricted to 0.5%. And for high temperature strength, because when two surfaces will rub against each other, it should have high temperature strength because temperature will increase obviously. So for that purpose, tungsten and molybdenum we need between 2 to 18%. And for hardenability, vanadium should be about 0.1 to 2%. And further, we increase the toughness by adding silicon. And now we discuss some concern in this high carbon steel and how it is solved, what is the remedy for that. So problem that arises is that like this, near eutectoid and hyper eutectoid plain carbon steels. Eutectoid, you must recall from the previous sessions, it was 0.8% carbon at a temperature of about 723 degrees centigrade. So in that case, these steels have tendency to lose hardness through tempering when rise in temperature occurs during the cutting. So it may happen that due to the temperature rise in the cutting process, this hardness will lessen, and the tempering effect will come into. So what will happen, the tool will get weakened. So we have to solve this problem. So for that purpose we will be using 1841 type of high speed steel, where there is 18% of tungsten, 4% of chromium and 1% of vanadium. And what do these do? These retain sufficient hardness due to carbide formation, which is a complex compound. Fe4W2C is formed. This is the chemical composition of the compound that is formed. So with the help of the chromium present in this particular SCS, that is high carbon steel, we will get a tough matrix. So toughness will also be retained, and these steel may retain hardness up to a temperature of 500 degrees centigrade. So they can retain hardness only up to 500. Above that, then the hardness goes down. So for that purpose we use this 1841 type of SS. Further we discuss high duty tool and die steels. What are these? So these are made of many different steels of fairly high alloying contents. So different elements are present in these, and high carbon, high chromium die steel will contain around 2% of carbon, 0.3% of manganese and 12% of chromium. And these are very hard actually, and unmachinable also in its hardened form. So cold machining is difficult in this case, and small and large carbide particles are there dispersed in the ferritic matrix on annealing around 800 degrees centigrade. So in annealed state, this steel can be machined with difficulty. So in the cold state it cannot be machined at all, but when it is annealed it can be machined, but there is difficulty. So this is an important requirement, because tools and dies have to be machined before they are hardened for final use. So we know that tools and dies have to be machined in the proper shape and all those things needed according to the process. So that's why this is very important. Annealing process is important before they are hardened for final use. Now we discuss about the magnetic alloy steels. So there are two types. One, that is steel that retain their magnetism, are termed the hard magnetic steels, and the other group is the magnetically soft one, the magnetic hard and the magnetic soft. So magnetic type, in the magnetic type 1% plain carbon steel in its fully hardened condition was the earliest permanent magnetic material, it is said. It contains high proportion of nickel, cobalt, aluminium and a small amount of tungsten. One example in this case is the Alnico, with 10% of aluminium, 18% of nickel, 12% of cobalt, 6% of copper and the rest is iron. The second type is the non-magnetic type. The first one we discussed was the magnetic type. In that also two gradations were there, soft and hard. So now we discuss the non-magnetic type. So examples for this are the earlier one is the iron and the iron silicon. So these are the non-magnetic type. Now modern high duty soft magnetic materials are the iron nickel alloys such as the permalloy, which contains 78% of nickel. Another soft magnetic material is mu metal, which contains around 75% of nickel, and the applications are that they are used for transformer cores as well as the shield material for submarine cables. So after discussing various kinds of stainless steels and high speed steels as well as the tool steels, we now share with you heat treatment of stainless steels. That is important, and why it is done actually? For stress relief, to remove residual stress occurring due to mechanical working. And what are the processes for this heat treatment? This is carried out by heating it to 370 degrees centigrade and then cooling at a low rate. So cooling should not be at a very high rate. And this treatment reduces the susceptibility to corrosion for this stainless steel. So corrosion susceptibility will reduce. But Resistance against corrosion cracking is improved by stress relieving at 770 degrees centigrade only. The first process that we are discussing here again is annealing. And what is the problem actually this stainless steel faces is that ferritic stainless steels are prone to form patches of transformation products, particularly after welding. So after welding, in case of ferritic stainless steel, there are certain transformation products which are in the form of patches, and they can break, or they are making a very rough kind of layer over the specimen. So the solution is like this. Annealing is carried out by heating this ferritic steel to 770 degrees centigrade as mentioned earlier, and it is cooled in a furnace or in air. So both types of cooling are permitted, either in furnace or in air. This treatment will stress relieve and homogenize the structure. So the structure will be homogeneous. Further, there is the process of solution annealing also. So in this treatment is given to austenitic stainless steel. When it is in the form of gamma austenitic stainless steel, then the annealing happens. So steel is heated from 1000 to 1120 degrees centigrade. And this austenite actually acts as a powerful solvent for chromium carbide and makes a homogeneous structure. So this kind of annealing is done for that purpose only. Earlier also we read that chromium carbide is not a very good thing, it leads to embrittlement. So again here the austenite is a very good solvent for chromium carbide, that's why we are using this solution annealing process. The chromium carbide structure is retained by quenching heated steel in water, oil or air depending upon the thickness of the section. And in some cases this is also retained if we want hardness up to a certain level, we want its retention. So for that matter this process is given. And air is the best quenching medium for thin sections. If we want thin sections, then we need air. The process is also referred as to quench annealing, this air cooling process. In this session we learned about different kinds of alloy steels which comprise of structural steels and stainless steels. Then we discussed about the different kinds of stainless steels also, and further we shall discuss in the next session. Thank you very much.